So in this video, we're going to look at problem 2.35, which is a pretty simple problem, especially if all of the problems up until now have been easy to you. Namely, we have a coplanar force system, meaning that we have two forces acting in two dimension. We're given both the magnitude and directions of each, and what we're asked to do is to determine the characteristics of the resultant force. Remember that the resultant force is just a fancy way to say the sum of all forces acting on a body. So similar to what we've done up until now, we're going to take both forces and we're going to decompose them. Once we have them decomposed, we will compute the resultant force by simply adding the like components. Particularly, they're interested in the magnitude and direction of the resultant force, so we will use trigonometry in order to determine what those are. One thing that I wanted to point out again, just in case you're only watching this video, is that when you do the decomposition of a force and you're given the angle, don't always think that the x component will correspond to the cosine of that angle. You always want to draw the force decomposition for whatever geometrical information you're given and kind of see how the side links relate to the specific angle that you received. So in this case, if you have F1 pointing up here in the first quadrant, note that the corresponding force triangle, which would have components along the y and x axis, the y-axis would go upwards in the positive direction of y, and the x component would go to the right in the positive direction of x. But relative to the angle that we're given, you note that the x component is actually opposite of that angle. So in this case, for the 30-degree angle, the x component will be related to the sine of 30, and the y component will be related to the cosine. Similar to always making sure that you're using the appropriate trigonometric function for the geometrical information that you're given, we also want to make sure that if we're just treating it as an equivalent triangle, that we adjust the signs of the components depending upon where that vector actually lives. So what I mean by that is if you were to draw a forced triangle to decompose F2, note that the x component would be in the positive x direction. However, the y component in this case would be the negative. The way that the text would traditionally treat that is in order to determine that y component, you would just take F2 and multiply by the sine of that angle since it's opposite. However, you would manually adjust the sign. You would put a minus sign on the front to denote the fact that that component goes in the negative y direction. So let's actually look at the solution here. And I've already probably said too much about it. You probably know how to solve it already. If you notice, I'm showing you the individual decomposition force triangles for both F1 and F2, similar to what we said. The y component is adjacent to 30 degrees. The x component is opposite. Both are in the positive direction, so I won't need to do any adjustments. I'll just take my magnitude and multiply by the sine or cosine of the appropriate angle, which is 30 degrees in this case. For the case of F2, note that the x component is adjacent to 20 degrees, so it would be computed by taking the magnitude times the cos of 20 degrees. No sign adjustment is necessary because that goes in the positive x direction. However, notice that the y component, which is opposite of the 20-degree angle, points in the negative y direction. So I'll manually put a minus on, and I will use the sine function since it is opposite of that angle. Once I have this vector decomposed into x and y components to compute its resultant vector, I simply add the x components and add the y components. If you do that, again, just carrying more precision than I need to avoid rounding error, I will get this x and y component. I always think it's good when you have the x and y components of a vector to actually sketch it. Notice that the x component of this is much larger than the y component. So, and in addition, x component is positive, y component is negative. So this is going to be a vector down here in the fourth quadrant that is going to be pretty close to the x-axis because it's got this huge x component in magnitude and the small y component. And the y component, of course, is going down. So in order to compute this angle, if we just look at what it would be, the y component will be opposite of that angle. The x component will be adjacent. So I can just take an inverse tangent of the opposite divided by adjacent side. And since by definition, when we report an angle from the positive x-axis that's rotated in the clockwise direction, we call that negative. I'm going to manually add on the negative sign. Alternatively, you could have appended the negative sign to the y component. So either way that you do it, you're going to get the same answer. I think it's always just easier to compute the physical quantities and adjust their signs manually. In addition, if I know the x and y component, note that I can compute the magnitude is just the square root of the sum of the squares. If you're still confused by that, that's just Pythagorean's theorem in action. The x component is the one base of a right triangle. The y component is the other base, and that magnitude is simply the hypotenuse of that triangle. So this is just Pythagorean's theorem, and this is just the TOA of SOHCAHTOA. So hopefully by now, all of this decomposition in two dimensions is becoming just secondhand.